Hello everyone and welcome back to my another video. Well, this video right now will be a little different from previous ones. Well, recently I was investigating and checking the wav2vec2 framework for self-supervised learning of speech representation. Well, that's kind of paper from 2020, and if you are related or doing something in speech recognition tasks, probably you already heard it. Well, this is a second version of this kind of paper. There was, of course, the first version, wav2vec2, simply, and this is a released paper from Facebook. And basically, what this is that's kind of paper that tells us how they released a model that is right now is one of the best in speech recognition models overall. Well, it's 3 years already for this model, but still it's one of the best models we can use. So basically, in this tutorial, I'll demonstrate you how easily we can fine-tune this model with our own data for speech recognition tasks. So I'm not going to cover the theory and the model specifications itself. I'm mainly gonna give you a code that I used to fine-tune our model on my own data with myself, my own tokenizer, and etc. This will be pretty simple, and we are not going deep into the theory or the coding stuff. I'll simply gonna cover it in short. So basically, that's pretty nice model because what we need to do is simply we read our audio data, we receive this kind of raw audio, and we simply feed this data straight into this model. And it has a convolution neural networks inside, transformer encoder layer, and there it gives us output. Well, basically this model is focused on CTC loss, and that's what I'm gonna use in this kind of tutorial and demonstrate how to use it as simple as it is. And we don't need to train this model from scratch. We can use the pre-trained model and we fine-tune on this model. So basically this paper demonstrates what they did, and they explain why they received such great results and etc. And we're gonna use it. Basically, we're gonna fine-tune this. Of course, there is some results of data that are labeled. They do some comparison on it, but I don't think that you are so interested on this. So basically, this model is trained and published on Hugging Face, and we can use it from this. And this is the base, and you can see that's the Facebook, and it gives us some explanations. And of course, in Hugging Face, you can find some explanations how they train this model and etc. So I'll give you a video tutorial how to train this model and how to run the inference when you want to deploy it, and if you don't want to use PyTorch installation itself there. So what we gotta do is simply jump into the code of my ML2 package that I was working recently and so on. So you might see that I have wav2vec2 torch tutorial here, and you might heard it right now. I'm not going to use tensorflow, and I will use a PyTorch, and at the end of this tutorial I will explain you why, and that's gonna be pretty simple. So what are the requirements from this tutorial is that you need Torch, at least this version, because I tested on it and I'm not sure if it will work on higher versions. And you need transformers, so you could download this pre-trained model. You need this ML2 package that I recently released, but I'll update the version that you're gonna use. And of course, ONNX, and there might be ONNX runtime. Okay, let's import this. That's right. And let's go straight to the training code here, and I'll give you explanation what I do here. So basically, I import many stuff. Most of the stuff is from my ML2 package. As you might see, there is a model, CTC laws that I use, data provider, metrics to track character error rate and word error rate, and of course some callbacks, early stopping, warm-up cosine, model 2 on the next tensorboard, so we could track the metrics, how it trained, and etc., and model checkpoint. And of course, there are some augmentations related to audio, so random audio noise, random audio pitch, and time stretch. I implemented these few augmentations to improve our data, to scale it, so our model would fit it better on it. So basically, what we do here, still have, as you can see, wav2vec2 for CTC. That's basically will be from Transformers library that we should have installed while using this, and there's a few more functions from PyTorch. So, but you don't need to focus on it right now. So what I'm doing here, as you might see, I download a simple kind of LG speech dataset. That's pretty huge dataset that has 30,000 samples of speech that are labeled. And what we need to do, we simply need to download them. And I use this kind of function to download it. So it will be placed in dataset, LDOT speech, metadata, and so on. So if I open my datasets, you can see that I have this data already downloaded. And it's pretty simple. So let's move on. So next, I have some here a vocabulary that this is the usual stuff that have this kind of characters inside this dataset. So what I need to do, I need to pre-process this dataset. So I read this metadata path, metadata file that uses a separator of the following, and I simply read the strings of transcriptions in. And what I do here, so I join this kind of labels and I use lower, as you can see. This means that I don't want to have capitalized characters, I lower all of them. That's for simplicity reasons, because of course, when we are trying to recognize speech, we don't care if it's a capital or not. So simply, it's way easier and to train the model when all characters are lower, and this simplifies our vocabulary that we need to use. So great. So then I use a data provider. That's very simple to TensorFlow data provider, and actually I inherited everything from the TensorFlow data provider, but you might see that it has some additional parameters as workers, use multiprocessing or not, and etc. So this time when we are working with sound data, it's really hard on the CPU side, because it needs to load all this audio from our disk. And if we need to augment it, it's even harder. So usually if you have a strong CPU, I recommend to use it with multiprocessing. But if there's something wrong, it can't be used on CPU. It will be used as thread pool executor and etc. It simply iterates all our data. So what we do here, so we skip the validation. I have the configurations here that you can dig in and check what it has and how many epochs I want to train, what will be my batch size, what will be learning rates, and etc. What will be warm-up epochs, whether I want to use mixed precision or not, and etc. There's many different things. And this config is saved along the model, trainable model. So let's move on. And as you might see, I'm gonna use this data preprocessor. This is audio reader. This means that it will read audio with sample rate of 60,000, and it will create a specific audio object of my MLTU object. Then we need to use label indexer that will label our characters into the integer representation, and then we need to use this batch post processors. So when we are training our model, we need to have audios, for example, 8 audios in one batch. So when we want to train our model, all these audios should be the same length. This means that we use audio padding, and I recommend to use this on batch, and then it will be padded to maximum size of possible length in the audios. And the same we apply for labels, and we don't need to pad. For example, if we have sentences with 20 characters, we don't need to pad it to 100 characters. It will be a little harder to train our model, so for efficiency it's better to pad only to the maximum length that exists in our batch. So this is the purpose of this, and this is, as I mentioned, is whether we want to use multiprocessing or not. And if we are training our model on some weaker CPU, it might not handle this very much. For example, on my computer, I can't use multiprocessing on Windows at least. But if I try to run this on Linux, it works. So it depends on what operating system you have, what CPU you have, and etc. And this is kind of very good worker that when we work with audio, because it will work in the background, load everything for a trainable model for us in the background. That's pretty amazing how it works. And there, of course, we split our data into validation and training, and we're gonna save this along the model what our training and validation data sets. So this means this is simply for validating our trainable model. And if we want, we can use augmentation, and I'm not using it because it eats a lot of CPU power, and it's pretty hard to train. It takes way more time to train augmented audios. So the crucial part right now is here. We need to create this wav2vec model from PyTorch Transformers. So basically, we use wav2vec2 for CTC, and we use from pre-trained. And as you see, I'm using pre-trained name, and this is the specific name from Hugging Faces. And we're simply gonna download this model and load it on. And what I'm doing here differently is that hidden states. I'm changing my the vocabulary size, and I ignore mismatches. This means that I'm changing the head of this model and simply put my own head that will be trainable for classification. And when we feed the forward pass, here we input our audio data, audio batches, and etc. And we simply receive the outputs, and we use the logits from these outputs into the logsoftmax function, and whole output will go to the CTC loss. Of course, you can implement this differently, but for me, I found this is pretty good implementation, so I follow with it. So here we create this custom model of PyTorch, and we have it here, and I put this on GPU because I'm totally not recommend to try to train it on CPU, because you're gonna need to wait months to train it, I believe. And of course, if you want to train it on pretty large data set, you need kind of very strong GPU, or use multiple GPUs, and of course pretty strong CPU. Remember that to train audio transformers on audio, it takes a lot of time, so it's up to you. So next we define the warm-up cosine design, and I'll explain what it does, but it's pretty necessary to use with transformers. So it means that we start from really low learning rate, and every epoch we increase this learning rate to faster and better train our model. So then I use the tensorboard. That's pretty self-explainable. We use early stopping. We track the validation character error rate, and of course we could track the word error rate, but I chose to use character error rate. It's up to you. What you want to do. So next I use a model checkpoint. This means that I'll save my models as model PT. This is the weights, and I will save the best weights according to validation character error rate. That's what I'm gonna use. And of course, at the end, I wanna save my best model into ONNX format, so I don't need to save the PyTorch model, because it's pretty hard when I'm using a PyTorch to load back the trainer model on another platform. For example, if I want to use this on Raspberry Pi, it's pretty impossible to load this back without knowing the architecture or without installing the PyTorch. So I chose to convert the model to ONNX, and then it's very simple for me to run this on any other device I want. So that's it, and here you might see that I have a custom model object that handles all the training stuff, the callbacks, the metrics, and etc. So here what I do here, I feed to this model a model, as you can see, custom model. That's my wav2vec model. I use CTC laws, and that's kind of custom lost, and we here use our vocabulary for this kind of data set. And then I use Adam B optimizer. You can use simple Adam. Both work well, but it was shown that Adam W works slightly better, so why not using it? And then I want to track my character error rate and word error rate. That's kind of usual when we are working with words, audio, or any recognition related to speech, words, characters, doesn't matter. Then I use a mixed precision. We can find it is in configs, and usually if you have good GPU, it will dramatically increase the training for you 2 times at least, and it will take less memory on GPU, so we can use larger batches, but it's up to you. I chose to use this mixed precision as true, and then I save this train and validation CSV files from my split, so later I could test how my model works that I train and convert on the next. So I want to use this on same validation data, because of course on train data it will work well. And that's it. We called the fit and we waited to finish. Well, I don't want to train it right now, because if I start training, my CPU jumps to 100 and I might face a blue screen, or simply the video recording might start lagging insanely. But to prove that it works, I can start it immediately and kill it when it starts training. So let's run and let's see how it keeps loading something here. Okay, and as you can see, it takes 1474 batches to train, and that's great. As you can see, it doesn't handle multi-processing, so it's switching to multi-threading. That's as I expected, because I know that it doesn't work on my machine like that. And within the first batch, it will be pretty good. Okay, and as you can see, it keeps training, and it shows us character error rate, word error rate, and we simply need to wait until it completes this stuff. But right now, because I'm recording, it's way slower, and I believe it might be lagging on my side, so I don't want this to continue training while I'm recording. So great, I'll kill it, because I already trained this model and I already tested everything out. Let's kill this stuff. Okay, I'll simply kill this one. So great, and I believe you're interested how it trained, how you can prove it. Okay, I have a pre-trained model, and if I go to my models, I have wav2vec2, and here is my trained model that already has PT weights and model on next. That's a trained model. But first, before going to the test part, let's look at the tensorboard, how it trained. And I have a tensorboard for exactly that, what I showed you. And let's maximize this one. And you might see that it started training, and there was 10 epochs of warm up, and it wasn't improving at all. So that's the worst part with this model, because it's training for such epochs and it's not decreasing, we are not sure whether it's training or not. But look at this, after 12 epochs it dramatically dropped somewhere here, and you might see that character error rate of training is 0.21 and validation is only 0.01. So that's a huge difference. And if we scroll to the end, you might see that it dramatically decreased. And let's look at the word error rate, because that's related to words. And you might see that at the end, our training was only 2% error and validation was 1.8 error. So this means that it works on our 8 audio data, and our loss looks exactly the same. So now let's look at our learning rate. So that's exactly what I was talking. What is this warm up. So this means that you might see that it starts increasing the learning rate to some learning rate we define. So this is 1.1e minus 5 is my learning rate that it should have achieved during the warm-up, and it achieved this, and it continued training, and it was decreasing, our word rate was decreasing, everything was just great. And it trained actually. Loss looks pretty the same, and we don't need to look at it. It was simply also was high, and then dropped dramatically. So great, it works. So right now you might ask, well, prove it that it works. Okay, great. Why not? So if I go to my Moodles, here I have a test.py script that I created, and here is my ONNX inference model and CTC decoder and character and word error rate calculation scripts. So what I do here, so simply here I have my model trained, you can see 434, and I load this model ONNX with my following object, and what we do here, how we do this prediction. So here is our audio path and the true label. So maybe we are interested to see what is the label. Great, not a problem. Let's print it out here. Print label. And it will print in terminal for us. And right now I read this validation CSV file that it was saved along the model here. And we're gonna iterate through it to see whether it works or not, and we'll see what are the true labels of it. And we are not interested in the prediction because this error rate is pretty low, so we might not notice the difference accurately without having time into it. So great. And if I run this for whole this dataset, and we will see what is the character and word error rate for my kind of labels, true labels, and etc. So let's run this simply, and you'll see that it's pretty nice and it works. So simply what we do, we use our LibRosa to load this up, and we load this audio. We have this audio raw data that we put into this kind of prediction model, and it expands them, runs the inference, and use a CTC decoder to decode the text, and that's it. And you might see here is the output of my models. And you might see that there is character error rate, word error rate, what are the results, and etc. And let's stop this right now. I'm not interested actually. And let's move on. And we can see what are the true labels. Oh, I see. It's not that perfect. I see it cropped me capitalized letters because all sentences start from a capital. So that's my problem. I need to change this train script to prove it that it works. And basically you might see that that's my mistake. I teach my model to predict speech without capitalized letters. So yeah, that's my mistake. I need to look at it closer. So anyway, I'll fix this training code for you. I don't know, maybe I'll train another model, but I'm not recording another tutorial right now because I'm not interested to do so. And of course, I'll publish all the model there into my GitHub repository and etc. You can find the link in the video description below if you want, and there everything is. But here is the idea, how simple it is to fine-tune this wav2vec2 model, and you can use audio wherever you want. So basically, it works, as you can see. And if you can try to record your audio and use the prediction, but it will be pretty hard and it will be not that accurate because this kind of data set that I used to train is very specific with a accent of people that were reading books, and it might be not that great for you, but still it works, and you can try to use your own data to fine-tune this model, and you'll see that it works pretty nicely. So, but I don't want to invest a lot of time into explaining this stuff here. So basically, it works. And if you like this video, please don't hesitate to smash the like button, subscribe, and if you have any questions, drop the comment below and you'll see how to solve this. So basically, let's go back to one stuff. If you remember, I do not recommend to train this on TensorFlow, and there is a huge problem with this, because we can load the transformers, the same model that we use in PyTorch, but there's a minor difference that training takes around 5 times longer. I don't know why. It uses the same CPU, same GPU as the PyTorch, but it trains way slower, and I can't explain this. So I don't know why we would like to train this model on TensorFlow if we can faster train it on PyTorch. And if we anyway are going to deploy this into some ONNX format and use it. So it's up to you. You can try to train this on TensorFlow, but I do not recommend to do so. I recommend using only PyTorch. So it's up to you. So that's it about this introduction with wav2vec, and this code you can find on my GitHub link in the description. And try to train your own model, or you can try to run my own model that I'll upload link also into description. So that's it about this, and that's it. We'll see you in our next video tutorial. Thank you again for watching, and we'll see you next time. Bye.